Hello everyone. In this video I'm going to be going over a couple of examples on finding power series solutions to a differential equation about an ordinary point. All right. So hopefully you've been reading whatever textbook you're in and know what it means for a value to be an ordinary point of a differential equation. I'll do a quick recap of what that means as well. Alright, so in this example, and I have two examples because these can take a while. And in each example I have the following instructions. So I'm asked to find two independent power series solutions of the given differential equation about the ordinary point x equals 0. Alright, so I guess I should talk about what it means for a value to be an ordinary point, especially for a second order equation. Right? And this definition can be extended to higher order equations as well. But if you put the equation in standard form, right, a homogeneous second order equation, so y double prime plus and then some function of the independent variable x times y prime plus some other function, say capital Q of x times y equals 0, a value x equals x sub 0 is an ordinary point of the differential equation. An ordinary point of the differential equation if both p of x, this function, this coefficient of y prime, and q of x are analytic. Analytic at x equals x sub 0. Right. Now, again, I'm not going to get all into, make this video all about series, and you should have been introduced to power series and series before, is what I'm assuming here. Remember, a function is analytic at a value x sub 0 if you can express that function as a power series centered at x sub 0. And again, I'm assuming you know what that means. In other words, the function is at x sub 0 and basically all its derivatives exist at x sub 0. Or, maybe the limit as x approaches x sub 0 of the function, and the limit as x approaches x sub 0 of all the derivatives of that function exist. But still, as long as you can express both of these functions as a power series centered at x sub 0, they would say that these functions are analytic at x sub 0, and if both of these coefficients here are analytic, then they would say that x sub 0 is an ordinary point. Alright, so just got that definition out of the way. Hopefully that's a refresher of your memory and you've read it before. Alright, so we're saying here, x equals 0 is an ordinary point of this differential equation here, right? It's already in the standard form, right? The coefficient on the higher order derivative is 1. The p of x and q of x here are just constants, right? The p of x here is 0, right? There's 0 y prime, and the q of x here is 1, right? The coefficient of y. Both constants, so very clearly both of these are analytic at x equals 0. I mean, they're analytic for any value of x, right? So really, any point is an ordinary point to this differential equation. Okay. So now I'm going to go about, hopefully maybe you saw I put up a video, if you've been watching, following. I put up a video on finding a power series solution to a first order equation. And being a first order equation, right, the general solution had a single parameter family of solutions. Well, now that I'm dealing with a second order equation, my general solution should depend on two parameters, right? Have two constants that we can freely choose in our family of solutions, and each constant will be attached to some independent, two linearly independent solutions. That's what I'm saying here, find two power series. Okay, now before I get into actually finding the power series solutions, let's solve this, the old-fashioned way, right? So I'm sure you've seen this method of solving an equation like this. So I'm going to put recall here. This is a homogeneous linear equation with constant coefficients. So you could solve this the old way. Call this the original way, the old way, and it's the quicker way, of course. Right? If I were asked to solve such an equation, I would do it this way, not with power series. You'd have the auxiliary equation. I would let y be equal to e to the mx power, and find some values of m that make this equation true. Plugging this in, just taking the first derivative, second derivative, substituting, you get the auxiliary equation m squared plus 1 equals 0, and the roots would be imaginary, right? Have an imaginary part to it, 0 plus I, 0 minus I. So the general solution, right, the general solution to this differential equation is y equals, and again, hopefully you remember how to get this, some constant, I'll call it a, times the cosine of x, plus some other constant, I'll call it b here, times the sine of x. All right. Again, hopefully that all rings a bell. And then what we're going to see when we go about finding power series solutions to this equation is that we'll end up with a constant times the power series for the cosine of x, plus some other constant times the power series for the sine of x. Right, and being that every point really is an ordinary point here, you're gonna also see that the interval of convergence for these power series is all real numbers. All right, we'll get to that later. All right, so now let's get to the power. Trying to find power series solutions to this. All right, and then this this method, right, of finding power series solutions is useful, especially when you have an equation that you don't know how to solve in some other way. Right, and that's actually going to be my second example. This first example, we could solve this kind of an older way that we saw here. In my second example, I'm going to simply add a coefficient that's not constant to one of these terms, and then, oh man, it'll be something that maybe you know how to solve it in some other way, maybe not, but let's just say that it'll be an equation that in general probably don't have any particular method for solving it in some old technique. So we're going to have to go through and find a power series solution, and it won't be nearly as clean as you'll see for this example. Alright, so let's assume that this does have some sort of power series solution. Let y equal the sum from n equals 0 to infinity of c sub n times x to the nth power, right? Your power series. And again, if you're unfamiliar with this, this would be c0, right, plus c1x plus c2x squared, etc. Okay. All right, then I want to eventually, substitute these into the equation here. So I need the first derivative, and I need to get up to the second derivative. Now the first derivative would be the sum from n equals 1, right? Because when I take the derivative of this constant c0, it's nothing. So having it start at n equals 0 is meaningless. It just adds another 0 term. So from n equals 1 to infinity of c sub n times n times x to the n minus 1, right? Derivatives of polynomials and stuff. So this would be c1 plus 2c2x plus 3c3 x squared and so on. And then finally y double prime. And this, for the same reason I started y prime at n equals 1, I'm going to start y double prime at n equals 2. Right. So from n equals 2 to infinity of n times n minus 1 times c sub n times x to the n minus 2, right, which would be 2c2 plus 6c3x and so on. All right. Okay. So I've got expressions for my derivatives and junk. Let's substitute them into the equation. So the equation is y double prime plus y equals 0. So y double prime was this sum here. Right, so this is a sub into the differential equation. So the sum from n equals 2 to infinity n times n minus 1 times c sub n times x to the n minus 2 plus y, so the sum from n equals 0 to infinity of c sub n times x to the nth. And this equals 0. Alright, now this is actually already set up kind of nice. If you recall again from an earlier video I've done, our goal is to take everything to one side, 0 on the other, and then I would like to write this side as an expression with a single series, not two series. So I'm going to do that by re-indexing. Now the nice thing is that both of these series start at x to the 0 power in their first term. So I can just re-index right now. Right, so I'll re-index these series. So in the first series, I'm going to replace, again, I'm just going to replace the powers. I want both series to be in terms that have the general term involve x to the kth power, so that they're the same. So I have k be equal to n minus 2 here, or you could say n is k plus 2. And in this series, I'm just going to replace n with k. So everywhere there's an n, I replace it with k. Let's see what we get. So the first series, I have the sum from, now when n equals 2, k would be 0. And as n approaches infinity, k would approach infinity. Right? So I have the sum from k equals 0 to infinity of, n is k plus 2, n minus 1 would be k plus 1. So k plus 2 times k plus 1, right, that's the n times n minus 1, but replacing m with k plus 2, times c sub n, but that's k plus 2 again, times x to the k. Right, then we have plus, and then again just the second series replacing n's with k's. Sum from k equals 0 to infinity of c sub k times x to the k. And this should all be equal to 0. And these are the same exact equation. If you write out a bunch of terms of these series and a bunch of terms of these series, you'll see they're exactly the same series. These are exactly the same expression. All right, and now I can put them together because we have the same index, right, both with k, and both series are starting with the same value. If that's the case, you can put them together, and I have this single series, the sum from k equals 0 to infinity. And I noticed again that both of these terms, I got these both to have x to the k on purpose, so I can pull that out. And what's left over is we'd have k plus 2 times k plus 1 times c sub k plus 2, and then plus c sub k, right, all that times x to the k. And this is equal to 0. Alright, now this is just for the purposes of this video. You don't have to do what I'm about to do here. But now that I've got this left side as an expression involving a single series, I'll write out the first several terms here. Right, just take a look at what this looks like. So when k equals 0, right, when k equals 0, it's be 2 times 1, so 2 times c sub 2 plus c sub 0. Right, and there's, times x to the 0. Plus, then when k equals 1, the next term, you'd have 3 times 2, so 6 times c sub 3 plus c sub 1 times x, plus, and then when k equals 2, right, the next term, that'd be 4 times 3, so 12 c sub 4 plus c sub 2, times x squared, and so on. Right, that would continue on forever. And we have just a giant, infinitely long polynomial on the left and 0 on the right. And if you recall from previous videos, again, the only way this is going to be true for all x here, the only way this is going to be an identity, a true statement, the only way a polynomial is 0 all the time is if all the coefficients are 0. Right, that's the only way this is going to be an identity true for all x. So, this previous statement here implies that all these coefficients must be 0. The k plus 2's, right, the k plus 2 times k plus 1 times c sub k plus 2 plus c sub k, all those must be equal to 0 for k from k equals 0 to infinity, right? So for k greater than or equal to 0. Now, in other words, right, we're basically we're trying to describe the sequence of constants, all these c's. And then once we've described these constants, we can go back and talk about what kinds of series satisfy that differential equation. So solving for the term further down, right, c sub k plus 2 would be the term further along in the sequence than c sub k. Right, this is two terms after c sub k. This would be the opposite of c sub k divided by, and then, k plus 1 times k plus 2, or k plus 2 times k plus 1, however you want to write that. Okay? Alright, and then, again, if you saw my video on finding a power series solution for a first order equation, I'm gonna start going through a bunch of these, right, until we start seeing a pattern forming. All right. So starting with k equals 0, we'd have c2 equals, basically just negative 1/2 times c sub 0. All right, it's replacing k with 0. All right, then when k equals 1, we'd have c3 would be equal to, negative 1/6, or negative 1 over. Now again, there's a reason I'm going to be writing this way. Negative 1 over 3 times 2, right? 3 times 2, k plus 2 times 2, k plus 1 times c sub 1. Again, I like to, maybe try keeping things factored for a while, and maybe we'll see some patterns forming. When k equals 2, and we got c sub 4 equals negative 1 over 4 times 3 times c sub 2. But if you recall, c sub 2 is negative 1/2 times c sub 0. So what I'm seeing here then, after substituting that, well, negative times negative would be positive, and then my fraction would be 1 over 4 times 3 times 2 also would be in the denominator, and then times c sub 0. Okay, so I think I'm seeing what's going on here already. See 2 factorial there, that's 3 factorial, 3 times 2 times 1, really. Here's 4 factorial in this denominator. I'm going to keep going. I'm going to put up several more. So k equals 3. So we have c5 equals negative 1 over 5 times 4 times c3. But again, c3, do this in a different color, is this expression here involving c1. Right, so I make that substitution. We have negative 1, positive, sorry, because you have negative here, negative there after making the substitution. Positive 1 over 5 times 4 times 3 times 2 times c1 though, right? So what I'm noticing here, just after these first 4, is that for even subscripts of c, c2, c4, that they depend on the constant c0. Whereas the odd subscripts of c, c3, c5, they're going to depend on c1. And so I'm seeing that there's going to be a 2-parameter family of solutions, and that should happen. This is a second order equation. Right. So one of my solutions will depend on c0. We'll have c0 attached, that constant. The other one will have c1 attached. All right. So again, I'll keep on. All right. So k equals 4. So we have c6 would be equal to. I'll do one more pair of these, and then we'll get back to writing out our power series solution and seeing how it's actually going to be a 2-parameter family of solutions. Right. So c6 would be, negative 1 over 6 times 5 times c4. But again, C4 was this, so it's negative 1 over 6 times 5 times 4 times 3 times 2 times C0. And then I'll just write out what the C7 will be in terms of C1. Hopefully you see that it's going to be negative 1 over 7 factorial times C1. I'm hoping you see that. All right. So in general, what I'm noticing here is that C sub n, right, the nth term of this sequence of constants, can be broken up into the following ways. It's equal to evens and odds, right? Say if n equals some odd number some even number 2k, then C sub 2k looks like negative 1 to the k power, right? Because for 2 times 1 it's negative, for 2 times 2 it's positive, for 2 times 3 it's negative, so negative 1 to the k power to alternate negatives over 2k factorial over n factorial 2k factorial times c sub 0. And if n is equal to some odd number, which can be represented as like 2k plus 1, right, so even up here, odd indices down here. So again, 2 times 1 plus 1, you have negative 1, it's a negative term. 2 times 2 plus 1, it's a positive term. 2 times 3 plus 1, it's a negative term. C sub 2k plus 1 is negative 1 to the k. Again, divided by that number factorial, n factorial, 2k plus 1 factorial, and then times c1 though, right? The constant c1 is on all these odd index terms. Okay, so now that we've seen the pattern, and again, that's probably, I think, the hardest part, and sometimes you can't. Sometimes you're just going to have to write out the first several terms and hopefully see the pattern. But sometimes it's hard to write an actual nice closed form for the pattern like I have here. And we'll see that actually in my second example. Alright, so the second example is going to be a little less clean than this first one's going to end up being. Alright, so now let's go back to our power series. Alright, and then substitute these into our series. So back to our power series solution, remember it was y equals the sum from n equals 0 to infinity of c sub n x to the nth. So if I write this out, and I'll write out a bunch of terms here. Remember, this would be c0 plus c1 times x plus c2 times x squared plus c3 times x to the third plus c4 x to the fourth plus c5 x to the fifth, and so on. And then substitute what I have found these constants to be equivalent to. Well, c0 is going to stay, c0. c1, I started here at c2, back up here when I was determining patterns. c1 is its own constant as well. c1 stays c1, so c1 times x. All right, and then we saw c2 was, negative 1 over 2 factorial times c0 times x squared, right? That was c2. Right? And then c3 was negative 1 over 3 factorial times C1 times x cubed. That was C3. And C4 was positive, 1 over 4 factorial times C0. Right, then you have x to the fourth. And finally here, C5 was positive 1 over 5 factorial C1, right, times C1, x to the fifth, and so on, right? And again, we have seen a pattern for both. Now I'm going to break it up. If I separate it to the parts of the series, we get y equals, separate the parts of the series that have C0 attached, this term, right, all the even-powered terms, and factor out C sub 0, I'd get C sub 0, right, times the following sum, times 1, then minus half x, minus x squared over 2 factorial, then plus x to the fourth over 4 factorial, then it would be minus x to the sixth over 6 factorial, and so on. Well, dot 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 there, plus, and then I start looking at all the terms with C1 attached, all these odd powered terms, and pull the C1 out, plus C1 times, and if I factor C1 out, you'd have x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. And then using my little expressions here from earlier, we can express this as the following: y equals some constant, c sub 0, and then this first sum I could express this way as the sum, kind of using my expressions from earlier, from k equals, now you could do, I guess, k equals 0. K equals 0 to infinity of negative 1 to the k over 2k factorial times x to the k, or x to the 2k, sorry, because these are all even powers. And verify that, when k equals 0, you'd get, 1 over 0 factorial, which is 1, times x to the 0 would be 1. When k equals 1, you'd have negative 1 over 2 factorial times x squared. When k equals 2, it would be positive 1 over 4 factorial times x to the fourth, and so on. So this series perfectly represents what I have in the box here, in the brackets here, plus, and then c sub 1 times, and then this series can be represented this way, the sum from k equals 0 to infinity, but involving odd powers, of negative 1 to the k over, and then 2k plus 1 factorial, and then times x to the 2k plus 1, again just to indicate odd powers here, alternating odd powers over odd factorials. And you can verify this, replace k with 0, you'd have, actually I should bump that up maybe. Now replace k with 0, that's positive 1, negative 1 to the 0. 1 over 1 factorial times x to the first, that term there. When k equals 1, it would be negative 1 over 3 factorial times x to the third, and so on. Alright, and then here are those two independent power series solutions. This one and this one. At the beginning of the problem, I was asked to find, two independent power series solutions. So these are two independent power series solutions of that differential equation. And then what we're seeing here is that any linear combination, some constant times this plus some constant times that, is also a solution of the differential equation. All right, so I've done it. And you can also verify, and I'll leave this to you, you can verify that the interval of convergence for both series is all real numbers. You use the ratio test, or maybe you recognize these as the power series for cosine and sine of x, right? But the interval of convergence for both of these series is all real numbers. Right? You can verify that as well. Yeah, I'll put this in a. But here we go. All right, there's the general solution to our differential equation written in terms of two power series. All right. Now, again, this is all great, and this one turned out very clean, very nice. And I'm hoping that you remember too. All right, like I said, I'm not going to go into power series all that much here, but the discussions. But I'm hoping that you remember that the power series I have here, this sum from k equals 0 of negative to infinity of negative 1 to the k over 2k factorial times x to the 2k. This is the power series, or the Maclaurin series, it's power series centered at 0 for the cosine of x. And this series here, attached to the C1, the sum from k equals 0 to infinity of negative 1 to the k over 2k plus 1 factorial times x to the 2k plus 1, this is the Maclaurin series, or power series centered at 0, for the sine of x. I'm hoping you recall that. So I get the same general solution as I got, the old way, using the auxiliary equations and whatnot. So y equals, some constant times the cosine of x plus some other constant times the sine of x is the general solution of our differential equation, right? Just written in power series. Now, this first example, everything turned out very clean. I could find the pattern for these constants, right? I could find a pattern for c sub n, but that's not always the case, right? It's not always going to be easy to see a pattern or write a nice closed form of the pattern for these constants. And same thing goes for, the equation we're given is not always easily solvable in some old method. Right? This one I could easily solve, find the general solution using the auxiliary equation. But again, that's not always the case. All right, so we'll see that right now. All right, we'll see that right now in my second example, where all I've done is change the coefficient on y from 1 to x. And now all of a sudden, this becomes a little more difficult. Right? Because I can't, this is now not, it's homogeneous, it's second order, it's linear, but it doesn't have constant coefficients. Right? It doesn't have constant coefficients. Now, it's in that standard form where the coefficient on the second highest derivative is 1. Everything's on one side 0, and the other everything else 0 on the other. The p of x that was brought up earlier would be 0 still, but this time q of x is x, not 1. But still, both of these are analytic at x equals 0. These are still polynomials. Polynomials are analytic everywhere. So these are still analytic at x equals 0. So x equals 0 is still an ordinary point. In fact, because these are polynomials, again, every point, every value on the real number line is an ordinary point. Okay. And then same thing as before, right? Same thing as before, only it might be, like I said, it might be a little trickier because we may not be able to see how to, write the pattern of the constants in some closed, neat way. And if that's the case, just write out the first several terms of the series, and so that maybe someone who's reading it can see the pattern and could continue the series on for themselves. So yeah, so I don't have any other. In previous videos I've posted for this, this differential equations course I'm teaching. Don't really have a way to solve this using other methods. All right. So I might have to. In that case, you probably would have to bring up a power series solution to the equation. Okay, so let's get to the power series. So again, I'm going to let, and it's the power series centered at 0. All right, now if you were doing this for power series centered somewhere else, you would just have it be centered somewhere else. But we're doing power series centered at 0, so I'm going to let y equal, again, the sum from n equals 0 to infinity of c sub n times x to the nth. And then our main goal is going to be figuring out what do these constants look like? What do these coefficients, these c sub n's, look like? And as before, being that it is a second order equation, I'm hoping to have it so that I can break it up to, a 2-parameter family. Maybe some will depend on one series will be multiplied by some constant c0, and the other series by another constant c1, right? Just like in the previous example. All right, and then we saw y double prime already, so we substitute stuff into this. So y double prime, remember, would be the sum from n equals 2 to infinity of n times n minus 1 times c sub n times x to the n minus 2. And then we have plus and then x times y, sum from n equals 0 to infinity of c sub n x to the nth equals 0. Now, x, because the only variable changing in these series expressions is n, x can be treated as a constant. I can put this inside. So this series can really be written this way: the sum from n equals 0 to infinity of c sub n times x to the n plus 1 power, if you want to put the x inside. Alright, now comes the part where I'm going to write the left side here as an expression involving a single series, not 2 series like I have. Alright, well, this series starts at x equals 0. And this series starts at not x equals 0, sorry, x to the 0 power. Starts at x to the 0 power. This series starts at x to the first power. I don't like that, right? In order to be able to put the series together and re-index, I want them to start at the same thing. Well, the highest of these is x to the first, so all I need to do is pull one term off of this series, and then I'll have another series that starts at x to the first. So if I take out the term when n equals 2, so when n equals 2, I get 2c2 x to the 0. So I get 2c2 plus, and then the sum from n equals 3 to infinity of this n times n minus 1 times c sub n x to the n minus 2. And now this series starts at x to the first as well, right? When n equals 3, you'd have x to the first power in your first term. Okay, and then plus, this series here, the series sum from n equals 0 to infinity of c sub n x to the n plus 1. And this is all equal to 0. All right, so now I'm going to re-index as before. So in this series, I'm going to have k replace n minus 2, which means that n is k plus 2. All right. And in this series, I'm going to have k replace n plus 1, right, with these powers on x. Or n is being replaced by k minus 1. Same thing. All right, now if I do this, we can combine the series. So I'm going to kind of skip ahead to where I combine them. This will be 2c2 plus, and then the single sum, where both of these will start at k equals 1. All right. Both of these will start at k equals 1. So from k equals 1 to infinity of, and then both of these will have x to the kth power, and I'm combining the terms. So here we'd have k plus 2 times k plus 1. All right, replacing n's with k plus 2 times c sub k plus 2 times x to the k, but I'm factoring the x to the k out. plus, and then c sub k minus 1, right? N is replaced by k minus 1 now over here. And all this times, x to the kth power. Right? And this is equal to 0. Now, as before, right, as in the previous example, the only way, now this is just one giant polynomial really, if you were to write all this out. And you can do that. You can write out the first several terms and say, hey, this is giant, it goes on forever and this giant polynomial is equal to 0. Well, the only way a polynomial is identically 0 is if all the coefficients are 0. Right, so from this line here, I'm getting the following. 2c2 would have to be equal to 0, right, implying that c2 must be 0. And all these coefficients here, these coefficients of the powers of x must be 0. So, and what I'm going to do is I'm going to solve right now for ck plus 2, right? This is the term that's further along in the sequence. It's actually 3 terms further down the sequence of constants than c sub k minus 1. So c sub k plus 2 must be equal to, negative 1 over k plus 2 times k plus 1 times c sub k minus 1, right? Or if you just put c sub k minus 1 in the numerator, whatever. Okay? And this is for, k 1 or greater, k greater than or equal to 1. Okay, and now what I'm going to do is just like before, just start putting in different values of k, and I'll do a bunch, right, until we maybe see some pattern forming, right? Now, it might not be a nice pattern that we can write a little formula for like last time, but still I'm going to do enough where I can see something going on here, right? Where I could continue it if I wished. Alright, so k equals 1. When k equals 1, we'd have, c3, right, equals negative 1 over 3 times 2, and then there's a reason I'm going to be writing this like this, times c sub 0, right? So I see that c3, right, depends on c0. Right, when k equals 2, we'd have c sub 4, the fourth constant, be negative 1 over 4 times 3 times c1. Right. So c4, I see, depends on the value of c1. So again, it's looking like some terms will depend on c0, some terms will depend on c1. Right? And I'll have this, again, a 2-parameter family of solutions. When k equals 3, we'd have c5 equals, negative 1 over 5 times 4 times c2. But remember, from up here, right, c2 is 0. So it looks like c5 is also 0. Alright. And I'm going to go out a bunch, right? So bear with me here. When k equals 4, we have c sub 6 equals negative 1 over 6 times 5 times c3. But remember, c3 is this term here. Right, c3 is this expression, so I'm going to replace c3 in this, and then I'll make it a positive 1 over 6 times 5 times 3 times 2. So if that's not exactly, now I'm seeing like 3 factorial there, but this is not 6 factorial. We're missing a 4. So maybe that'll come into play. Right? I'll just write this right now as I'm c sub 0. Just keep that in mind. Let's see if I can mess with that later. Alright, then when k equals 5, we have c sub 7 equals negative 1 over 7 times 6 times c4. But again, c4 we know the value of. We have an expression for that from earlier. Right, here's c4. So I'll put that in here. Right. And that makes this positive 1 over 7 times 6, but then times 4 times 3. And then times, c1. So again, not quite 7 factorial. We're missing a factor of 5 and a factor of 2. But still, it depends on C1. Again, we're seeing that some constants will depend on C0. Some constants will depend on C1. Alright, so I'm going to go just a few more. I'll get another pair. Now, we'll see that C6, or when k equals 6, sorry, C8 be negative 1 over 8 times 7, times C5, but C5 was 0 because C2 was 0. So it looks like every third constant, from C2 onwards, C2 is 0, C5 is 0, C8 is 0. It would seem that C11 would also be 0, right? C14. Looks like all those are going to be 0. Okay, k equals 7. All right, just a couple more. I'm just going to do a couple more. We'd have C9 equals negative 1 over 9 times 8 times C6, but this was C6. So replacing this with C6, negative 1 over 9 times 8 times 6 times 5 times 3 times 2 times C0. So again, it's not quite 9 factorial. It's missing a 7 and then 4 and 1. Right. Okay. Alright, so I'm seeing something here, right? We're missing every third factor. 7, 6, 5, 4, 3, 2, 1. Here, 5, and then 4, 3, 2 is missing. Okay. So k equals 8. We'd have c sub 10 equals negative 1 over 10 times 9 times c sub 7. This was c sub 7. So it'd be negative 1 over 10 times 9, skip 8, times 7 times 6, skip 5, times 4 times 3, skip 2, and then times c1, right, replacing c7. Okay. And then one more, when k equals 9, right? C11 is going to be 0. Right? We know this because it's going to involve C8, which was 0. Right? C8 was 0, and so on. Okay. So I guess I could break this up into 3. I'll keep this to go forever. I could break this up into 3 things based on the value of the subscript here. So like if you're a multiple of 3 or a multiple of 3 plus 1 or a multiple of 3 plus 2. Okay. So it looks like so C sub 3k, right? If we're a multiple of 3, be equal to. Again, this is just me kind of trying to figure out a little pattern for this. You'd have negative 1, I'll say negative 1 to the k, right? Because 3 times 1 has a negative, 3 times 2 is positive, the negative 1 to the second, 3 times 3 is negative. And then, it's going to depend on C sub 0, right? All these multiples of 3 depend on C0, right? C3, C6, C9. And then bear with me here. And think about what this is missing in the bottom to make it 6 factorial. A 4 and a 1. So if I multiply the top and bottom by 4 and 1, or just 4 times 1 over 6 factorial. And then this one, C9, what's missing to make this 9 factorial? It'd be 7, 4, and 1. So this would be the opposite of 7 times 4 times 1 over 9 factorial times C0. So it's looking like you start with 1 and then add 3 k minus 1 times, if I'm doing, I should maybe have made this like a j or something, but I go 1 times 4 times all the way out to 1 plus and 3 times k minus 1, which would be 3k minus 2 when you put it all together. Let's see if that works. When k equals 1, we just have 1, stop at 1. When k equals 2 for C sub 6, that'd be 3, 1 times, stop at 4. When k equals 3 for C sub 9, you stop at 7. Right, and then divided by 3k factorial. But you see how ugly that is? This is the pattern I'm seeing though. Right. In fact, I might not even write this out. I'll just write out the first several terms with these coefficients here. So that's what I'm seeing when we have a subscript or an index that's a multiple of 3. Then when we have an index, maybe I should write this on another page here. When we have an index that's a multiple of 3 plus 1, right, like C sub 4, C sub 7, C sub 10, right, some multiple of 3 plus 1. Again, thinking about C sub 4 there, this is almost 4 factorial. I would have negative 2 on the on top, and then 4 factorial times C1. And then C sub 7 is missing 2, then 5. Right, so 2 times 5 over 7 factorial times C1. And then C sub 10 is negative, and then missing 2, 5, and 8 over 10 factorial times C sub 1. Again, if this doesn't make sense, I apologize, but I'm just trying to see patterns here. Again, I eventually just might end up writing the coefficients the way they look. So it looks to me like if your subscript is some multiple of 3 plus 1, you'd have negative 1 to the k, right, alternating negatives, divided by that 3k plus 1, divided by that subscript factorial. And then up top, you're multiplying by 2, then 5, then blah, blah, blah. And keep that pattern going until you get to, and you just keep adding 3, and you add 3 k minus 1 times again. So 2 plus 3 times k minus 1, 3k, up to 3k minus 1. 3k minus 1. And then times c sub 1. And again, double check this. This c sub 10, that's 3 times 3 plus 1. So the value of k here would be 3. Be negative 1 to the third, negative, and then 2 times up to, you keep this pattern up to 9, up to 8, which is what's going on here, over 3k plus 1 by 4. This works out. Again, if you're not seeing that, don't worry. Right? If you're not seeing this, don't worry about it. You can actually just write out the coefficients as is. And then finally here, if your subscript is a multiple of 3 plus 2, that coefficient 0, right? Like C11 is 0. That's a multiple of 3 plus 2. C8 is 0, a multiple of 3 plus 2. C5 is 0. C2 is 0. Okay. Okay. Great. Now let's actually go back to our series. All right. I'm going to go back to our series here and write these coefficients into our series. All right. So back to the power series. We had y equals, sum from n equals 0 to infinity of c sub n, x to the nth. And again, I'll write out a bunch of these. We have c0 plus c1x plus c2x squared plus c3 x cubed plus c4 x to the fourth plus c5 x to the fifth plus c6 x to the sixth plus c7 x to the seventh, dot dot dot. All right. Now c0 is just c0. c1 is just c1, so c1x. c2, remember, is nothing. Now c3. Right, c3 was this thing here, right? I'll put minus 1 because again, I don't feel like you can write out the crazy pattern if you see it, but I don't see the. If you don't see the pattern, you can just write out the numbers themselves. This is minus, so c3 is minus 1/6 times c0, and then times x cubed. C4, same thing. I wrote out this weird pattern here. If you're a multiple of 3 plus 1, you don't have to write out this pattern. It just C4 would be negative 1/12 times C1, and then times x to the fourth, and then C5 was 0. And then C6 would be a 1 over 180 because it's 30 times 6, so positive 1 over 180, C0, right? X to the sixth, and then C7, and this will be enough, and then I'll spread them out and just write dot dot dots everywhere. And then C7, right, we saw was I think 504 because it's 10 over 7 factorial. Well, this is just 42 times 12, which is 504. So this is 1 over 504 times C1 times x to the seventh, dot dot dot, right? And then plus 0, right? Because C8 would be 0, and so on. All right. So as before, you can do. I see that my series here is a 2-parameter family, right? The parameters being c sub 0 and c sub 1. So you get y equals, c0 times the following sum. If you look at all the terms with c0, c0 there, c0 there. So it's every multiple of 3 power, right? Every multiple of 3 power. And if I pull c0 out, you'd have, 1 minus 1/6 times x cubed plus 1 over 180 times x to the 6th, then minus and dot dot dot. All right, and I'll just do this. All right, that's totally fine. Plus, and then all the terms with c1 attached, or all these ones with a multiple. The power is a multiple of 3 plus 1. Right, 1 more than a multiple of 3. Pull out c1 times, and then we have the sum x minus 1/12 x to the 4th plus 1 over 504 x to the 7th minus dot dot dot, and there we go. All right. And also, I would leave it to you. I will leave it to you. Now, if you figure this out, what a general pattern is. The interval of convergence for this series is all real numbers again. But I'll leave that to you to figure out. And here are your two power series, right? This 1 minus 1/6 x cubed plus 1/180th x to the 6th, blah, blah, blah. That's one of the power series solutions to this differential equation. Here's another one. X minus 1/12 x to the 4th plus 1 over 504 x to the 7th, and so on. So this is totally fine, right here. Describing the general solution to the differential equation in power series. And again, it's not nice, it's not clean. Now, if you actually saw the pattern I set up earlier, you could also have done this, right? Or y equals let's see, would that work out for those coefficients? Like if k were 0, no, not at all. So this has got to be for k is greater than or equal to 1. Okay, so we got to start these as c3, third power and 6th power. Same thing here. All right, so I could do this as well using my little formulas that I wrote up earlier, right? Those crazy expressions. This thing for when the subscript was a multiple of 3, and this when the subscript was a multiple of 3 plus 1. Right. So I could also do this if I wanted to write a series. All the stuff with c0 would be y equals c0 times the expression 1 plus, and then the sum from k equals 1 to infinity of that crazy stuff here, this negative 1 to the k times 1 times 4 times dot 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 times the pattern here up to 3k minus 2 divided by 3k factorial times x to the 3k power. And again, you can verify that if I write, when k equals 1, this is negative 1 to the first, so negative. And then this pattern up here would stop at 3 times 1 minus 2, so it would stop at 1, so times 1, divided by, and then 3 factorial, which is 6, so you get negative 1/6 x to the third. And then when k equals 2, you get this positive 1 over 180 x to the 6th, and so on. Plus, and then c1 times, and again, I gotta keep x there. It doesn't work for the coefficient on x, but then the rest of it does. Plus the sum from k equals 1 to infinity of negative 1 to the k times 2 times 5 times all the way up to whatever 3k minus 1 is, divided by 3k minus 1 factorial times x to the 3k minus 1. And again, you can verify that this series does work. So you got the x there, and then when k equals 1, right, this is negative 1, and then this multiplication pattern stops at 3 times 1 minus 1, so it stops at 2, so you got the times 2 in the numerator divided by, divided by 3, oh, sorry, it was 3k plus 1 factorial down there that I wrote. All right, and then divided by 4 factorial, 2 over 24 is 1/12. So this is negative 1/12, and then x to the 3k plus 1 power. Right, it's a multiple of 3 plus 1. That'd be x to the 4th power. And then when k equals 2, you have x to the 7th, and this would end up being, positive 1 over 5 over 4 when k equals 3, and so on. So, and then the interval of convergence, again, you can use the ratio tests on these, and you could probably, I'm hoping very easily verify that the interval of convergence would be all real numbers. All right. So you could also have written this out if you saw it. Again, if you don't see that pattern stuff, I'll say it one more time. If you don't see it, I'm totally fine with if you hand in something to me. If you're in one of my classes. If not, don't worry about it, obviously. But if you can't see a pattern like this, figure out how to word it, how to show it in some expression like this. Writing out the first several terms of each series, and then adding a little ellipsis at the end is enough for now. Because again, the solution isn't very clean, it isn't very nice, and this is probably the best way you can express it. All right. So yeah, so that was a lot. Over an hour this video. I apologize for the length, but you can see that finding a pattern, figuring out what's happening with these coefficients is difficult sometimes, right? It's also very tedious, can take a while. So thus the length of the video, right? I only did 2 examples here. So I wish you luck when you're working on stuff like this on your own. Hopefully watching me work through these couple helps you out, helps you when you're trying to work on problems similar to this. And thank you very much for watching.